Good morning. Welcome to the video lecture on design of RCC elements. In last class, we have seen about the limit state design, that is the limit state of flexure, that is for beams. We have seen about the singly reinforced section, how to analyze the singly reinforced beam, then what is meant by singly reinforced beam and doubly reinforced beam. Then we have seen one problem related to singly reinforced beam. Okay. Let me have a small brief introduction about the limit state method for flexure today. After that, we'll continue the session on doubly reinforced section. Singly reinforced section, doubly reinforced section, we have two types of sections. So as far as the beam is concerned, in limit state method, we are designing a beam, then we need to check the beam whether it is safe or not. Then that safe is nothing but whether it is over reinforced or under reinforced, or else it is under balanced section. Then what type of failure we would be expecting for a beam after designing your section. Okay, right. In singly reinforced beam, the beam which is reinforced in one layer, that is your main tensile reinforcement will be happened over there, where your stress is been acting in tension side. That is, if suppose take this is as beam, this is the central line is your neutral axis, this half part will be subjected to compression, below the neutral axis the half part will be subjected to tension. That is, this beam is capturing load in the perpendicular direction of your axis, horizontal axis. This part will be subjected to compression. That is, this concrete area will take care of your compression, right? Then below your neutral axis, this is, here we are providing a steel layer, this bottom side. So this tension part, if it has been expanding, when you are capturing this load, it has been expanding, this tension part will be taken care by your steel. That's what we know. The steel will be good in tension and bad in compression, whereas concrete is good in compression and bad in tension, right? So the steel will take care of all your stresses and strain in the bottom portion of your, below your neutral axis part. Okay. You may ask some questions like this. You can say singly reinforced is nothing but only providing reinforcement only in this region, not here. You may have some doubts like that. The answer is providing steel in the tension reinforcement, that is the main motto. Then here we need to provide reinforcement. I won't say that I won't provide any reinforcement here. This reinforcement won't take care of your tension. Here this reinforcement will act as a hanger bars. Hanger bars in the sense, I want to provide a shear stirrups around my main reinforcement layer. So box type layer will be provided as a reinforcement, that is called a shear reinforcement. To hold my shear reinforcement, I need two bars to be laid down at the top region also. That bars we can call it as hanger bars in case of singly reinforced section, right? Okay, let me come to doubly reinforced section. Doubly reinforced section is that providing reinforcement in compression region and also in tension region. Why is it so? You can ask me, why is it so? Why we need to provide two layers? First thing, while designing your beam, you need to check whether the moment, actual moment for your beam, which is less than your limiting value or greater than your limiting value. That limiting value is depend upon, we can call it as MU limit. That MU limit which depends upon your providing steel, what are the amount of steel you've been providing in your section. Based on your XU max by D, we have written IS 456 page number 70. We have some criteria. XU max by D, it is been changing, depends upon your stress in your steel. When Fe 250 you are providing, you have a XU max by D value. Then for Fe 4 and 5 it is 0.48. Then for Fe 500 it is 0.46. For Fe 250 it is 0.53. So when the gradation is increasing, that is the grade of steel Fe 250, 4 and 5 and 500, when the grade is increasing, your XU max by D value is getting decreased. From the XU max by D value, you will be calculating the Mu limit value. Mu limit value is also based on your grade of steel provided in your section, right? Okay, what is your Mu limit? We all know now. Mu limit is nothing but the limiting moment of resistance provided as per your adopted steel. Okay, then what is your actual Mu? Actual Mu is nothing but for your provided section, say for example 300 by 600, I have provided some 1600 mm square steel. For that, what will be my moment? That is the actual moment of my section. When my actual moment of my section is less than the Mu limiting value, then it is safe. Okay, what is the actual value? That is small when compared to the limiting value, then it is safe. We can proceed our section as singly reinforced section. No need to provide your reinforcement in compression zone, only provide your reinforcement in the tension zone. Okay, okay. Or else when my Mu is greater, that is actual Mu is greater, then my limiting value is lesser, I need to go for redesign of my section. That is, the limiting value is somewhat 220, my Mu is about 520, it is more. It needs to take care of my design. So, I need to go for two options. One option, that is, I can redesign my section. Redesign my section is nothing but I can rearrange my size of my beam. That is one criteria. The second criteria, I can go for providing compression reinforcement in the compression zone also, so that some part will be taken care by the compression reinforcement. This is the another way. Okay, the two ways, that is, one is redesign my section. When a client asks me not to redesign my section, I want the same section, you need to detail for that same section. If is it so, I can go for the second option. The second option is providing compression reinforcement. That is, providing compression reinforcement is nothing but we are calling it as doubly reinforced section. Okay, now it will be clear, I think so. Providing compression reinforcement and tension reinforcement, that beam we can call it as doubly reinforced section. Okay, when and why we can choose this doubly reinforced section? That is one of the major thought given in the designer's view when I want to choose my beam as doubly reinforced section. Okay, we'll see now when and why I need to go for doubly reinforced section. One thing, when I have some headroom requirements, that is headroom restrictions is nothing but when I can't able to change my depth. When depth is the restriction, I can't able to change my depth. The client says I need to provide same depth, it should be unique throughout my room, so that is the headroom requirements. In that case, we can go for doubly reinforced section. Or else, I want to increase the stiffness of my beam. If the stiffness is low when it is singly reinforced, I need to increase my stiffness. That is, my Mu is greater, I need to increase my stiffness. I can go for doubly reinforced section. Or else, compression steel, we are providing compression steel for doubly reinforced section. What it will do when we are putting compression steel in the doubly reinforced section? It will increases the rotation capacity of the beam, then it will also increases ductility. Why we need these two elements? When our structure is subjected to seismic forces, it is the lateral force acting along your structure. When your structure is subjected to seismic forces, lateral forces, it will be deflected in this fashion, right? So, it will induce some rotation capacity. To increase my rotation capacity, I can go for compression steel. Or else, my ductility is being ensured by providing compression steel. So, the ductility can be enhanced by means of compression steel, so that my structure will be safe under lateral loading condition. I can say like this. This is the question 1 and when and why I am using doubly reinforced section. Okay, let me go for the analysis part. For example, this is the beam of breadth B and depth capital D. Okay, here we all know AST is your area of steel in your tension reinforcement. This is my effective depth D, whereas this is your effective cover, that is effective cover. Okay, now this is what there in your singly reinforced. Now we are providing additional reinforcement, that is called as ASC, area of compression steel. This is area of tensile steel or area of tensile reinforcement we can call. Now the same way effective cover, here also this effective cover I can call it as D dash. Okay, now this value will be D, this is my whole D minus D dash. This region will be D dash. I can take the lever arm distance between the ASC and AST, you can call it as D minus D dash. I can call in this way also. Okay, first coming to the strain block. Strain block parameters. As of now, we all know that we have created some assumptions while starting my session in limit state for flexure. That first assumption is that the maximum strain taken by the concrete is 0.0035. The maximum strain occurred by my steel should be greater than or equal to 0.85 by Fi divided by Es plus 0.002. Then 0.002 is nothing but proof strain value. This is the allowable value of strain given for my concrete, whereas this is the maximum allowable limit of concrete to take up by your strain value. Okay, now we'll see the stress block. Now we'll see about the stress block parameters. We all know the stress block parameters for concrete. The design stress, the maximum design stress is 0.45 FCK, where I have got these values from my, this is my stress, this is my strain. This value, when I am taking compression strength of the concrete in cubes, I will take FCK. The compressive strength of my section, that is 0.67 FCK. This is due to size effect of my section. For the design curve, I need to take 0.45 FCK. This is FCK divided by 1.5, I will get 0.67, divided by 1.5, I will get 0.45 FCK. This value is the maximum stress allowed for my concrete, that is 0.45 FCK. Okay, till that this 0.002 proof strain, I will get some linear value. This is this linear value. After that my strain is been like parabolic fashion, right? Up to this I will get some straight line. After this the curve will be changing around. This is the stress block for my concrete. Here you may ask why you don't put any stress block over here in my tension region. Okay, in my assumption I have told you that my tensile strength of concrete should be ignored here. The concrete won't take any tensile strength, so that you should ignore here. Only providing steel to take care of my tension. So the tensile force Tu is nothing but 0.87 times Fy into AST. How I will get 0.87? This is the stress strain for my steel value. This is linear when I tested my steel value. This is Fy, that is my yield strength of my steel. When I go for design stress, I need to Fy divided by 1.15. This is 0.87 Fy. This is my design stress of my steel value, that is 0.87 Fy into AST. Now in singly reinforced section, for this stress block I will have only Cu value. Here I am providing steel in the compression zone also, that's why I may have CSU then CCu. This CCu is due to concrete, this CSU is due to steel. Okay, so this distance will be d dash. CCu is equal to 0.36 FCK XU into B, that is area 0.36 FCK. This is my XU, this is my B. Okay, then CSU, that is the force due to compression steel, is FSC, that is yield stress in my compression steel into area of steel, that is FSC into ASC, right? These are the stress block parameters, strain block parameters for my doubly reinforced section. Now I can write TU as 0.87 Fy into AST, CU, total CU may be CCU plus CSU, that is 0.36 FCK XUB into FSC into ASC. Now to maintain my section under equilibrium position, I may equate Cu is equal to Tu. So I can equate these two equations. So Cu is equal to Tu. Okay. Then I will use these conditions. My condition is, if you take the mu value, that is the actual mu of my section, when this actual mu is greater than my mu limit, you need to proceed this section. Okay. Take down the annexure G, page number 96 of IS 456 code book. In that code book, we can able to see the moment of resistance for rectangular sections formula, whereas how to calculate the depth of neutral axis from my equation XU by D. Then when XU by D is less than the limiting value, I can go with this equation. Then when XU by D is equal to the limiting moment of section, I can go with this equation. Okay. Then when we are provided the section with compression reinforcement, that is mu limit, it has been exceeding, I can go for mu minus mu limit is equal to FSC ASC into D minus D dash. D is your effective depth of your tension steel, D dash is your effective depth of your compression steel. I can go with these formulas. Okay, right. Here I will calculate my moment of resistance. Mu is equal to 0.36 FCK XU into B minus, this is my lever arm, this is Cu into Z. This Cu into Z. Z is nothing but D minus 0.42 XU plus your compression steel ASC FSC into D minus D dash. D minus D dash is nothing but lever arm distance. From these value I can calculate my actual moment of resistance. That is, I have written in a separate form, that is what is my lever arm, Z is equal to D minus X bar. This is my X bar value. The X bar value, the centroid of my compression force. This is my compression force into 0.42 XU plus FSC ASC into D dash divided by, this is like X bar A1 X1 plus A2 X2 divided by A1 plus A2, right? This is my area, this is my X1, that is the distance travel. This is my area, this is my distance travel, so divided by A1 plus A2. This is the formula for calculating centroid of my compression force. Okay, then I can write from the tension side, I can write my mu as 0.87 Fy into AST into Z. Then I can get from my code book mu minus mu limit FSC ASC into D minus D dash. Now let me clear the actual mu to be taken for my doubly reinforced section. Then what is the area of reinforcement we can call? We can call at the bottom it is AST, at the top that is ASC. How to provide the two types of reinforcement? AST1 is nothing but area of my tensile reinforcement. We can write mu1 divided by 0.87 Fy into d minus 0.42 Xu. We can take in this fashion, that is for tensile reinforcement. That's why we are using the tensile stresses over here. Then AST2, that is the additional tensile reinforcement to counteract your compression steel. So mu actual minus mu limit divided by 0.87 Fy d minus d dash. This is to counteract my compression steel. From this formula I can able to calculate AST2, that is my additional tensile reinforcement. That one we can also call in this way ASC FSC divided by 0.87 Fy. So I can write ASC as mu actual minus mu limit divided by FSC into d minus d dash. I can also write in this fashion. From this value I will be getting like this. The equation is like this. Okay. Here some concrete area is being lost now because I am be putting compression steel in the compression region. In the region occupied by the steel, some concrete area it has been lost. That area I can take in this manner. What is the amount of concrete area that I want to deduct it? That is ASC in this fashion MUD FSC minus 0.446 FCK into D minus D dash. This is the formula. This is for providing compression steel. This is the loss of concrete area occupied by my compression steel. Okay. Now I can calculate AST as AST1 plus AST2. This is the total tensile reinforcement, whereas another thing ASC I can calculate directly as AST3. Okay, these are some of the steel you need to provide for your doubly reinforced section. Now we'll go through quickly the problems related to problem type 1. A RC beam 350 mm by 750 mm subjected to superimposed bending moment of 400 kilonewton meter. Design the beam and adopt M20 FE 4 and 5 D dash as 50 mm, that is the effective cover to my compression steel. This is what the question like this. In this question they didn't mention it is singly or doubly, they didn't mention anything. They have given you the size, that is 350 mm, 750 mm. They have given you one small slight click is that the D dash value is 50 mm. Here also the steel is there. We have a neutral axis AST ASC. Okay. Now they have given you the bending moment of 400, that is superimposed bending moment. While calculating for limit state section, I need to have ultimate bending moment, that is mu, that is equal to 1.5. This is the factor of safety value. I need to multiply for my superimposed bending moment into 400. Now I will get some 600 kilonewton meter. Okay. Now what is the first step I want to do is that I want to calculate what is the percentage. Design is that I want to calculate the percentage of reinforcement provided, that is for ASC and AST. For that, first step 1 is that XU max by D. XU max by D for Fe 4 and 5 steel, it is 0.48. It is there in page number 70 IS 456. Okay, it is there from your code book. You can collect your value. XU max by D is equal to 0.45 for Fe 4 and 5 steel. Okay, then after getting this value, I can calculate mu limit is equal to 0.36 FCK XU max by D into 1 minus 0.42 XU max by D into BD square. I'll get around, I can substitute this 0.48 FCK, that is 20 is given, B I know, small d also I know. Now I'll calculate the value as 473.6 into 10 power 6 Newton mm. This is my mu limit, right? Mu limit. Okay. Now I can able to calculate what is the PT value from my XU max by D. Okay. PT is equal to, I have a formula 0.414 into 20, that is your FCK divided by 15 into 0.48. I'll get around 0.956 percentage. This is the allowable PT for my section. Now I can take AST1 is equal to PT, that is the limiting value from XU max by D into BD, that is equal to 0.00956 into 350 into 700. I'll get around 2342.2 mm square. Okay. Now I can directly calculate AST2 as MUD minus mu limit divided by 0.87 Fy into D minus D dash. This MUD I know, that is they have given us 600 minus 473.6 divided by 0.87 into 415 into 700 minus 50. Now I will get AST2 as 538.6 mm square. So I can add these two. AST is equal to AST1 plus AST2, that is equal to 880 mm square. Okay, 2880 mm square. Now I can able to calculate the compression steel ASC. I know the formula MUD minus mu limit divided by FSC into D minus D dash. I can get around 0.1945 into 10 power 6 divided by FSC. For this FSC, I want to calculate the value for the steel. So I want to take epsilon SU, that is strain value 0.0035 into XU max minus D dash divided by XU max. I can get around 0.00298. Okay, from the code book I'll directly pick the value of Fe for 4 and 5. The FSC value is 353.7 Newton per mm square. Okay. Now after getting this value, I can able to arrive my AAC. Now my AAC will become 549.9 mm square. Then I have calculated AST1 2. I can add up, this is the total amount of reinforcement to be provided as a tensile reinforcement. Then AAC also I have got. Then the last one, the loss of concrete area. ASC is equal to MUD minus mu limit divided by FSC minus 0.446 FCK into D minus D dash, that is equal to 564 mm square. This is the loss of concrete area. In this area I have provided the steel region. This is the same area, so I can able to cross check it. Okay, 464. Okay, these are the problem related to. We may have some different types of problem. I have done a design, entire design on doubly reinforced section. The problems may be from how to take the bending moment. When it is simply supported, we can directly take WL squared by 8, that is the how to calculate the moment value, or else how to calculate the depth of neutral axis. These are some of the how to calculate the area of compression steel alone and tensile steel alone. You may have some problems like that also. Okay, this is the standard procedure for calculating the design of doubly reinforced section. Okay, now we have seen what is mean by doubly reinforced section, when and why I want to use my doubly reinforced section, then what is singly reinforced, when it goes to completely as doubly reinforced, then I have arrived the stress block parameters, strain block parameters for my doubly reinforced section. After that I have designed a problem related to my doubly reinforced section. Okay, in next lecture we will see about the flanged sections of my beam. Thank you.